Everyone, Forces Screencast 2. Let's do this. The ideas that I'll be talking about today are acceleration without speed, gravity, and orbits. You need to do notes, and same as last time, you'll find the notes at the bottom in the video description. You need to either make a copy of this document and fill it out, and then print it out and put it in your notebook, or you can take notes directly into your notebook. That is your choice. Okay, vectors. Vectors. So acceleration is a change in velocity. Velocity is a vector. A vector has both magnitude and direction. The magnitude of velocity is speed. So when you change speed, you accelerate, right? If you slow down or if you speed up, you're accelerating. But also, you are accelerating if you change directions. Okay? So if you change directions, then you will be accelerating as well. So let's look at this guy. He's not changing his speed at all. He's staying in the same spot. There is no change in position, but he's changing his direction a lot, and that's resulting in a large acceleration and a large force. Not very smart, but a good example for talking about this. He was okay. All right. Oh, another cool thing. I just want you to watch this video, and we'll talk about it more in class on Wednesday, but just think about it. How is this happening? How is this possible? This is not photoshopped. This is really what's happening. Okay? So just think about it for a second. Just think about it for a little bit. All right, moving on to gravity. Gravity is one of the four fundamental forces of nature. The fundamental forces of nature are the forces that hold atoms together, that explain how galaxies interact, stuff like that. And we're only going to look at two of the four fundamental forces, and today we're going to talk about gravity. And Einstein came up with the idea of gravity when the apple fell from the tree, and blah blah blah. You know that. But how he defined gravity is a force of attraction that exists between all things that have a mass. All things, yes, all things. Between me and my computer, yes. Between me and the computer at school, even though I'm at home right now, yes. All right, all things have a force of gravity between them, but it is dependent on two things. Right? The force of gravity depends on mass. The larger, the more massive an object is, the more gravity there is. All right? And then the closer objects are to each other, the more gravity there is that happens between them. All right? And gravity always happens between things. It's not just something that something has on its own. It's something that happens between things. Okay. Einstein had a little bit different definition of gravity that is a little bit more accurate, and his definition of gravity affects influences both time and space and energy. And so, to make it simpler, Einstein talks about gravity as kind of this idea. There's this idea of space-time fabric, and it's a really cool visual. So you can see that we have this Earth, and the Earth is sinking into the fabric of space, and that sinking into the fabric of space is its gravity, right? And so the closer you are to Earth, the more you experience its gravity, the more you get sucked into its gravity. The farther you are away from it, the less you feel it. And so that's kind of how Einstein did it and talked about it. Okay, force pairs. So we just learned that for every force, there is a equal and opposite force. All right, for every action, there's an equal and opposite reaction, and this is true with gravity. So when I jump off the ground, I am pulled back down with a force of gravity to the earth. But what we don't think about is when I jump off of the ground, the earth is pulled towards me with an equal force. Okay? So if we look here, right? It doesn't matter if one of these is small and one of these is large, the amount of force is equal. Now, that doesn't really make sense. How can that be? How can it be that we have that the earth is experiencing the same force that I am experiencing, because the earth doesn't come up towards me, right? Well, it has to do with inertia. Inertia. All right? The Earth has a huge mass. It has a mind-blowingly large mass, right? The amount of mass that Earth has is crazy. And so we remember that force equals mass times acceleration. So if both the Earth and I are experiencing the same force, and the Earth has an enormous mass, then its acceleration is going to be almost nothing. Okay? And now that's different than me, who I have a very tiny mass compared to the Earth. Very, very tiny. Okay? Flip this around. I have a very tiny mass compared to the Earth. So that means that my acceleration is going to be way bigger, right? I'm going to have a huge acceleration, okay? And that's because I have a small mass and the force affects me a lot more than it affects the Earth. Affects the Earth, okay? Hopefully that makes sense. Moving on to calculating the force of gravity. Here's the equation. It's right here. Force of gravity is equal to the gravitational constant times mass 1 times mass 2. So in this case, it could be the mass of the Earth times my mass divided by r squared, which is the distance between the two objects squared. So in this case, it would be the distance from the center of the Earth to where I am right now. Okay? And we're going to be calculating the force of gravity. And that's why you're going to need to practice your calculator skills. And the gravitational constant, what is that? Well, sometimes in science we have constants, and these constants help us with units so that units work out to be correct, and they also help us so that our calculations give us numbers that make sense. So that's my best explanation for that right now. Here are Earth's stats. Earth has a mass of 6 times 10 to the 24 kilograms. It's a lot of zeros. And it has a radius of 6.4 times 10 to the 5 meters, right? And so let's think, if I'm calculating the force between myself and I'm here and Earth, I use this radius to calculate that force. Finally, orbit. We've heard of orbit. We are in orbit around the sun. Did you know the sun is in an orbit around a supermassive black hole at the center of our galaxy? There are thousands of satellites, man-made satellites, that orbit the Earth. But what is orbit? How does it work? That's what we're going to talk about right now. So think about this. If I took a cannon and I shot a cannonball, that cannonball would fly for a while and eventually it would get pulled down by the force of gravity. But now imagine I have a cannonball and I shoot it, a very powerful cannon from a very high mountain, and if I shoot it fast enough and hard enough, it will actually go all the way around the Earth. And this pretty much is what orbit is, right? It's when you have an object that's traveling so fast that it isn't going to be pulled down to Earth. But if it's traveling too fast, then it will actually fly away from the gravity of Earth, okay? And so an orbit is the repeated path, repeated, so it happens over and over and over. One object takes around another object in space. And so let's look at this. Clear, reset. We've got here Earth and the sun, and the Earth goes around the sun every 365 days. But why doesn't it just fly off into space? Why doesn't it just fly off into space? Well, it's because of gravity. All right, and so the gravity is pulling Earth towards the sun, but the Earth is traveling so fast that it's staying in its own orbit. If the Earth were to slow down at all, then maybe it would eventually be pulled into the sun. If the Earth were to start going much faster, then it would maybe fly away from the sun. But if I turn off gravity, then it will fly away. So I'm about to run out of time for video length. That's everything for today. Good luck. Watch Study Cat for good study luck. Meow. All right, talk to you soon.